Some record. All right, we'll go ahead and get started. Okay. Okay, pretty much everyone's turning in their second assignment. Okay, do want to remind you about the second exam that's already available on WebAssign. The due date for that is this coming Saturday, so make sure you have that done. And it pretty much only covers chapter 8. Okay, that's all. Okay, we'll pick up where we left off on Monday. And I think I stopped on conditional probability, and I was talking about where is denoted as the probability of B given A, which is how it is, how we read the notation. We did problem 5, E, F, and G, which is part of problem 5 that's similar to the one that's in your book and also the one that's in the homework, because they do give us the Venn diagram that you see up here. And E, F, and G ask for the probability of event A will occur given that B has already occurred. And we pretty much did those examples, those problems there. Okay. All right, next we'll look at the we'll look at determining the probability of event A and B for any events. Okay. Because here, these are so pretty much out of order. Okay, that's okay. All right, let's say we had this. Let's say an experiment. We have this experiment consisting of drawing 2 marbles from a jar one at a time without replacement. And if you recall, when we say without replacement means is this. The first marble is drawn and is not put back into the jar. Okay. And that's going to pretty much reduce the number of marbles that we have in that jar. Okay. So here the jar contains 3 blue marbles, 2 green marbles, and 1 yellow marble. Let's say we want to find the probability that the first marble is blue and the second marble is green. Okay. All right, so what that means is that the probability of drawing a blue marble on the first draw is going to be 3 out of 6. Because if you looked at the illustration that we just had, there were 3 blue marbles and there was a total of 6. So 3 out of 6 would be the probability of drawing a blue marble. And then the probability of drawing a green marble on the first draw would be 2 out of 6, because there were 2 green marbles in the jar out of 6. But let's say, in this case, given that the first marble selected is blue, then that means the probability of drawing a green marble, given that it was a blue marble that was drawn out, would be, now this time it's going to be 2 out of 5 instead of 2 out of 6. Okay, because, and I also can show this on the, I can show this on the board here. There were 3 blue marbles and 2 green. And I think there was a yellow marble in there, but since I don't have a yellow marble, I just use orange as this illustration. Okay. So in this case here, the probability of drawing a blue marble, that was 3 out of 6. And the probability of drawing a green marble, that's 2 out of 6. Okay. And in this case, the probability of drawing a green, and we're given that we have a blue marble already drawn out. Okay. So a blue marble is already drawn out. I'll circle that. That means that there are 5 marbles left. So that denominator is going to be 5. And the probability of getting a green would be 2/5. So that's where the 2/5 came from. Okay. So the event that the first marble is blue and the event that the second marble is green are what we call dependent events. Because knowing the first marble is blue affects the probability that the second marble is green. And of course it affects it because it does drop the sample size down a bit. Questions on that? Okay. And I'm going to skip over some of this right here. Well, I can talk about some of this right here. Of course, there's 6 marbles chosen on the first draw and then 5 chosen on the second draw. If we were to use what they call the fundamental counting principle, or now the fundamental multiplication principle, because what you're doing here is multiplying 6 times 5. And that's possible pairs of marbles. And there are 3 ways to choose a blue marble on the first draw and 2 ways to choose a green marble on the second. Okay, so that's going to be 3 times 2 or 6 ways to draw a blue marble and a green marble in that order. So in this case here, the first marble is blue and the second marble is green. Well, that's of course 3 times 6 for the probability of getting the first marble being blue. And then given that the first was blue, the probability of drawing a green marble on the second draw would be 2 out of 5. And that's where this comes from. Probability that is blue would be 3/6. The probability of green given blue would be 2/5. Okay, and that leads to this definition here, where we have A and B being 2 events. The probability of A and B would be the probability of A multiplied by the probability of B, given that A has already occurred. And this agrees with the one for independent events, because A and B are independent events. If they are independent events, then A does not affect the probability of B, which means that the probability of B given A will automatically be probability of event B. Okay. But this is for what they call dependent events. Now, if they were independent, then this right here, the probability of B given A would automatically be probability of B. So you'll just have the probability of event A times the probability of event B. Okay.
That's a bit dependent.
Yeah, that's for dependent. Any other questions? Okay. In this example, Mikey has 24 pens in the container. He knows 5 of the 24 pens are defective because they do not have any ink. Now in part A, Mikey randomly picks 1 pen. What is the probability that the pen is defective? And in part B, he randomly picks two pens, 1 at a time, again without replacement. What's the probability that both pens are defective? Okay. He knows 5 out of the 24 pens are defective. So, well, in A, the event that the first pen is defective. B, the event that the second pen is also defective. Okay. So if the first pen, he only draws 1 pen out of that container, the probability of him drawing a defective ink pen would be 5 out of 24 because there are 5 pens that are defective out of 24. Now in part B, he's going to pick 2 pens. And of course, there's a decimal, that's 20.8. I mean, yeah, percent. All right, now in part B, this is where we use the probability of A multiplied by the probability of B, given that A has already happened. Okay, 1 at a time, he draws 2 pens. The first pen will be defective, the second pen will also be defective. So here's how we compute that probability. On the first pen that first one that he draws is a 5 out of 24 chance that it would be defective. But on the second draw, we want to assume that it is also defective. So now, on the second draw, if the first one was defective, that means there are 4 defective pens left. And instead of 24 pens being left, there would be 23 left. Okay, so the probability there would be 4 out of 23. And we're going to multiply the 2 together. Okay.
So if you were going to modify the question to say the first one wasn't defective, but the second one was.
Okay.
That wouldn't change the second number.
No, it would not.
Okay.
Because if 5 out of 24 were defective, that means that 19 out of 24 were not.
Okay. Sorry. Yes. Got it.
Okay.
But it's still be 4 out of 23. Because we were trying to find the second, or it'd be 5 out of 23.
Yeah.
Okay.
Mm-hmm.
Got it.
Okay. Any other questions? Okay. And as a decimal, what they did was they might have did this 5 times 4, which is 20, and then the denominator 24 times 23. I'm not sure what that was. How much? 522. And then did 20 divided by 522. 552, I mean. So 20 divided by 552, and then times 100 would be approximately 3.6%. Okay. So this is numerator times numerator, then denominator times denominator. That would be 20 over 552. And then convert that to a percent, you'll get 3.6%. So the probability that both pens are defective would be approximately 3.6%. Okay. All right, any questions about example 25 and how that's done? Okay, question.
Multiply to both
Numerator times numerator, and then denominator times denominator.
Okay, 100 and 552. then what else we do?
Oh, 5 times 4, that's 20.
Uh-huh,
Okay, you do 20 divided by 552, and then times 100 to get the 3.6%.
okay, yeah, I got it.
Okay, any other questions? Okay, now, let's say, okay, this is problem number 15 here. The probability of event A is 0.24. Probability of event A is 0.24. And the probability of event B was 0.55. And the probability of B, given that A has occurred, was 0.3. So now we want to compute the probability of A and B. The probability of A and B. Okay. Now, assuming that we're dealing with dependent events here, the probability of A and B, that definition that I gave you on one of the slides is this, the probability of event A, and then that's going to be multiplied by the probability of B given A. Okay. So now we just substitute what the probability of event A is. Okay.
And 0.3.
Okay. Because we already given the probability of B given A is occurred. So we just multiply those two.
0.072.
It'd be 0.072. Okay. 0.072 would be the answer for that. Okay, for the probability of A and B. All right, any question about problem number 15? I just did. Okay. All right, now on to number 16. All right, let's say that the probability of A was 0.35. The probability of B was 0.22. And the probability of B, given that A has already occurred, is 0.15. And here I want the probability of A and B.
4. 4.
What was that?
4.
Oh, or. Oh, my. Thank you. So it's A or B. Okay. Now we did talk about the formula for the probability of A with or B. Okay. And that's this. Probability of event A plus the probability of event B. And then we have to subtract off A and B. The probability of A and B. That's the formula that we have to use here in this case. All right, now let me bring down the probability of event A plus the probability of event B. Because I know something about the probability of A and B. And that's this right here. Probability of A and B is this, the probability of A times the probability of B given A. So I'm going to substitute this with what that's equivalent to. Okay. I know that's hard to see with the computer in the way, but does everyone get what I'm doing here?
Yes. Substitute.
Okay, the substitute. Now let's do some substitution with these values here. Probability of A is 0.35 plus the probability of B, that's 0.22 minus probability of A, that's again 0.35 times the probability of B given A, that's 0.15. Okay. I'm going to work inside the bracket here. Bring this down, and that's minus 0.35 times 0.15.
0.0925.
Okay. Then I'm going to do 0.35 plus 0.22 minus 0.0525. And that would be how much?
0.5175.
Okay. 0.5175. That would be the probability of A or B. Okay. All right, any questions about problem number 16? Okay, now let's take a look at problem number 22. And it says here, statistics published in the San Diego Union Tribune show that 60,000 police officers, or 10% of America's cops, are hurt in the line of duty every year. Of the injured, 25% will become permanently disabled. Determine the chance that a randomly selected police officer, part A, is hurt in the line of duty. And then part B becomes permanently disabled given that the officer is in the line of duty. And part C is hurt in the line of duty and becomes permanently disabled. Okay, so let's kind of look at this particular problem, and I'm going to use some variables that will help us determine those probabilities. I'm going to let H be the individual that's hurt. And then D would be those who are permanently disabled. So in part A, we want the probability that a randomly selected police officer is hurt in the line of duty. Okay, that should be easy, 10%. Or as a decimal, 0.10. Because you're told 10% of America's cops are hurt in the line of duty every year. And now part B, the probability that the person becomes permanently disabled, that's D, given that the officer is hurt in the line of duty. All right, in this case, that's also an easy answer there, right there. Because it does say of the injured, how many become permanently disabled? 25%. So that's the answer to part D right there. Because given that they're hurt, 25% are permanently disabled. So that probability will be 0.25. All right, questions on part D. All right, and now part C. The probability that a randomly selected officer is hurt in the line of duty and becomes permanently disabled. Hurt and disabled. Okay, so we have to use that formula, that definition that I gave you earlier. Yeah. Probability that the individual, the police officer is hurt, times the probability that the police officer is permanently disabled, given that he or she was hurt. So the probability the individual was hurt, 0.10, times the probability of being permanently disabled, given that the officer was hurt, that's 0.25. So 0.10 times 0.25 is how much? 0.025. All right, any questions about problem number 22? Okay. All right, now, oops. All right, let's say we had this. Church groups and college sports teams are often used, they often use 15-passenger vans for transportation. The following two-way table is known. The following two-way table of known injuries, severity of occupants in a 15-passenger van involving single vehicle crashes for 1990 to 1992. And that's based on the federal report released in 2004 by the National Center for Statistics and Analysis. All right, so in this case here, that's going to be the table that we're going to be using. And I'm going to go ahead and recreate that table on the board, because on the very next slide, we're going to be answering a couple of questions that are related to that. Restrained. and total. The top is fatally injured. And survived. And the total. Okay. All right, so now we're going to use this to answer these questions here. Suppose an occupant in a single vehicle crash of a 15-passenger van is randomly selected. And we want to know what is the probability that the occupant was fatally injured, given that the occupant was restrained. And then part B, what is the probability that the occupant was fatally injured, given that the occupant was unrestrained? Okay. See, this two-way table is going to help us answer these questions here. So we're going to start off by finding the probability that the person was injured. Okay, so we're going to say fatally injured. And that's given that the occupant was restrained. Okay. Now, one of the things about conditional probabilities is this. Okay. All right. One of the things about conditional probabilities is this. It does reduce the sample size. Okay. Because in this case, we're given that the occupant was restrained. So the only thing we're going to be looking at is this row where the occupant was restrained. Okay. Now, the total number of people or occupants that were restrained, that's going to be 1,150. That 1,150 is a denominator. And out of the 1,150 that were restrained, how many were fatally injured? 95. That goes in the numerator. Okay. That's going to be the probability of a randomly selected passenger or randomly selected occupant was injured fatally, given that he or she was restrained. Now let's say we want that as a percent. It'd be approximately 8.3%. Okay, so there is an 8.3% probability that the occupant was fatally injured, given he or she was restrained. Okay, so that's part A. All right, now part B says this. We want the probability that the person was fatally injured. Fatally injured, given that the occupant was unrestrained. Okay, so we need to look at the row for unrestrained. Now I have to do this in orange. So it'll be this up here. Unrestrained. The total number of unrestrained occupants was 2,333. And out of those 2,333, how many were fatally injured? 517. That would be your numerator.
So when you're in more car crashes, more deadly.
Mhm. All right, so what would be this fraction as a percent? 22.2%. So given that the person was unrestrained, there is a 22.2% chance of that individual being fatally injured. Okay. All right, any questions about that particular two-way table? Okay, so this helps us reduce the probability when we're dealing with conditional probabilities. Okay, so the next thing we can look at here is using a tree diagram to represent and analyze probability problems. Sometimes we can use tree diagrams. Okay. All right, the main idea of a tree diagram is to represent the outcomes using branches or line segments and represent probabilities using numerical labels on the branches. Okay, so the definition there is, it is a representational tool for systematically organizing the outcomes and probabilities of probability problems that involves several stages. Okay. So here's how we can use a tree diagram in this situation. Let's say jar 1 has 2 blue marbles, 3 yellow marbles, and jar 2 has 3 blue marbles and 1 yellow marble and 5 green marbles. Okay. Now let's say that the marble is randomly drawn from jar 1 and then placed in jar 2. And then a marble is drawn from jar 2. What is the probability that both drawn marbles have the same color? Okay. So in this case here, this is where we can construct a tree diagram for this situation, as you'll see on the next slide. Okay, this is what figure 6 illustrates. Here we list all the possible outcomes from the first draw and the probability for each outcome in this stage. So on the first draw, we have like a yellow or a blue marble in the first jar. So those are the possibilities there. The probability of getting a yellow marble would be 3 out of 5. And the probability of getting a blue marble would be 2 out of 5. Because if you recall, and I'll go back to this slide here, in jar 1, there were 2 blue marbles. That probability is 2 out of 5. There were 3 yellow marbles. That probability would be 3 out of 5. That's where those probability fractions come from. Okay, so that's going to be on the first draw. This is what the first draw represents. Now on the next slide, it's going to be extended to this. I may need to move this out of the way. You know, Can y'all see this? Yeah, okay, good. All right, here are more branches that are created in this figure. Now you're given that the yellow marble is chosen from jar 1 and placed in jar 2. Now in jar 2, there was only one yellow marble. If a yellow marble is placed in jar 2, this time you only got 2 yellow marbles now. So the probability of getting a yellow marble is now 2 out of 10. Because now instead of 9 marbles in jar 2, they're now 10. Okay, everyone's okay with that. And then if the first marble is yellow, the probability of getting a blue marble would be 3 out of 10. And if the first marble is yellow, then the probability of getting a green marble out of jar number 2 will be 5 out of 10. Okay. Now let's say for this one, on the first draw, it was a blue marble. And you put that blue marble in jar number 2. There's a total of 10 marbles, but this time, instead of actually 3 out of 10, there will be 4 out of 10. Okay, so here, the probability of getting a blue marble out of that second jar, instead of 3 out of 10, it'll be 4 out of 10, because that blue marble from the first jar was put in the second. Now for the yellow, there's still only one marble, one yellow marble. That's 1 out of 10 for that probability. And there were 5 green marbles in jar number 2. So that's going to be 5 out of 10. Which is, if I can get this, okay, that's down here. Okay, so that's how we construct a tree diagram for this particular situation. Okay. And on the second branches, those represent conditional probabilities there. And to complete the tree diagram, we list all the possible outcomes and assign a probability for each outcome. Okay, so like the outcome Y and Y represents that the first marble is yellow and the second marble is yellow, given the first marble is yellow. Okay, so that's, in this case, it would just do the multiplication there along that branch. So it'd be 3/5 times 2/10, which is 6/50. But drawing a yellow marble on the first draw and then drawing the second yellow marble, given that we drew the first one to be yellow. And similarly, the outcome for Y, B, yellow, and then blue, we just multiply those probabilities along the branches. 3/5 times 3/10, or 9/50. And this is what the total, what the whole outcome is, all the outcomes and their respective probabilities. And this is probability under here. So in this case here, 3/5 times is 2/10, that's this right here, or 6/50. 3/5 times 3/10, that's 9/50 for a yellow and a blue. And then yellow, then green, 3/5 times 5/10, and so on. So this is the complete probability tree diagram for that. So we can use this to help us find out the probability that both marbles have the same color. And if you were to look at this, here you have a Y and a Y, they're both the same color, a blue and a blue, they're both the same color. The probability of getting a yellow and a yellow was 6 out of 50. The probability of getting a blue and a blue would be 8 out of 50. So on the next slide, you'll see you're gonna have to add those probabilities here. So we add 6 over 50 plus 8 over 50. That would give you 14 over 50, or as a percent, 28%. So the probability of both marbles having the same color would be 28%. Questions on this particular illustration? Okay. Now let's look at example 28. A jar contains 4 blue marbles and 2 yellow marbles. Marbles are drawn randomly, one at a time, without replacement until a yellow marble is chosen. So here I want to determine the probability of the following events. Exactly 1 draw is needed, exactly 2 draws are needed, and exactly 3 draws are needed. Okay. I'll tell you what, I'll go ahead and do this on the board and draw that tree diagram in its entirety from beginning to the end. Okay. Okay.
I like the right ones.
Okay. Okay, let me start with the tree diagram. Now we're dealing with my notes are out of whack. Here we go. We got 4 blue marbles, 2 yellow marbles. Okay. So here's how we draw the tree diagram. B will be blue and Y will be yellow. Okay. For the probability of drawing a blue marble, it would have to be 4 out of 6. And the yellow marble, that probability would be 2 out of 6. That's on the first draw. And then on the second draw, it would be blue or yellow. But notice here, if this blue marble was drawn at first, how many blue marbles will I have left? 3. Out of a total number of marbles, there have to be 5. And of course, the yellow marble, there's still going to be 2 because the first one was blue. But I'll have 5 marbles left because the blue marble was drawn first. And then let's look at this one. If a yellow marble was drawn first, I can draw either a blue or a yellow in the second. If the yellow one was drawn, I'm still going to have 4 blue marbles out of 5. Now, if the first one was yellow and the second one was yellow, that probability of drawing the second one yellow would be 1 out of 5 because I have 1 marble left, 1 yellow marble left after drawing the first marble to be yellow. Okay. And then if there was a third draw, I believe, a blue or a yellow on each one of these. So if the first one was blue, the second one was blue, then I'll be left with 2 out of 4. And the yellow, I'll still have 2 yellow marbles, but they'll be out of 4. If the second one was yellow, the blue, first was blue, it'll be 3. The second one was yellow, it'll still be 3 out of 4. And I'll be down to what, if the second one was yellow and the third was yellow, I'll be down to 1 marble, 1 yellow marble out of 4. And then the first was yellow, the second one was blue, and the third one was blue. This will drop to 3 out of 4. The first was yellow. This one was blue. I'm gonna have 1 yellow marble to draw out of 4, because the first one was yellow. And if the first was yellow and the second was yellow, I still have, in this case, 4 out of 4. And I only had like 2. So the first was 2 yellow marbles. So the first was yellow and the second one was yellow. I won't have any marbles to draw on the third pool. So this is up to 3 cases, because this will help us answer A, B, and C. Exactly 1 draw is needed. And this is until a yellow marble is chosen. So on 1 draw, which is right here, that's this first one, the first draw. The probability of getting a yellow marble will have to be 2 out of 6. Because notice, the probability of a yellow marble on the first draw will be 2 out of 6. And this is the second. This will be the third. And then part B, exactly 2 draws are needed to get a yellow marble. So we need to find out the ways that we can get a second marble to get a yellow marble. Okay, and that would be this one right here, the blue and the yellow. That's this one right here. Because we have to look at this right here. We can't look at this one because the first marble is yellow. We want to focus on the yellow on the second draw. That's this, from a blue to a yellow. That's 4/6 times 2/5. Okay, and by the way, 2/6 as a percent would be 33% approximately. For this one, if I do 4/6 times 2/5, this would be 8 out of 30. And as a percent, it would be 27% approximately. And then the probability of getting a yellow on the third draw. Let's see. The only way that could happen is that the first has to be blue, the second one has to be blue, And then the third one has to be yellow. So we multiply those probabilities along that branch. 4/6 times 3/5 times 2/4. And this will be 4 times 3 times 12, that's 24 out of 120. Which is, of course, actually 20%. All right, any question about example number 28 and how that's done using that tree diagram? Okay. All right, and the rest of these. Now here they use a partial tree diagram for this one. 4/6 for the blue, and then the yellow would be 2/5 to get that 27%. And then here we need 3 draws. The first has to be blue, the second one has to be blue, and then the third one has to be yellow. So that's where the 20% comes from. All right, now let's take a look at problem number 6 on page 522. In this case here, the tree diagram for an experiment involving drawing colored marbles is shown. Here I want to list the outcomes and the corresponding probabilities. Okay. Does everyone have this right up here? Okay. So I'm going to copy this particular all right. And he won't list all the outcomes and their corresponding probabilities here. Okay, so here we go. Starting here, we got a B and a B. So that means from a B to a B, we have to do 3/5 times 5/8. And let's say I want this as a fraction in simplest form. Well, I know something here, these 5s divide out. That'd be 3 times 1, which would be 3, over 1 times 8, that would be 8. So in simplest form, that probability there would be 3/8 for drawing 2 blue marbles. And then the other branch will be from a blue to a yellow. So here, this will be 3/5 times 3/8. So I have to do 3 times 3, that's 9, over 5 times 8, that's going to be 40. So that probability there of drawing a blue and then a yellow would be 9 out of 40. All right, Now here we go from the green to a blue. Just G and then B. That probability there would be 3/5 times 2/7. This will end up being 6/3. Wait a minute.
So I had 2/5.
Oh, I'm sorry. No wonder I copied it wrong. This should be 2/5. So this will be 2/5 times 2/7, which is, this will be 4/35. I apologize for that. Okay. And then a green and a green, that's from here to here. That's going to be 2/5 times 1/7. This will be 2/35. And then finally, from a green to a yellow, this will be 2/5 times 4/7. That'd be 8/35. Okay. So these are all the outcomes, all the possible outcomes, and their corresponding probabilities for each one of those. All right. Any questions about just listing those possible outcomes there? Okay, I'll tell you what, let me go ahead and stop right here, because the very last problem, number 7 on page 522, I'll pick up with that there. And then we'll go into 9.3 dealing with expected value and odds and the normal distribution. Okay, I'll cover that on Monday. All right, don't forget about exam number 4. The due date is Saturday. In web assign. Make sure you complete that.
You're not gonna finish homework yet, though.
Not yet. I'm gonna hold off on that. That way y'all can concentrate on your exam.
Thank you.
All right, you too.